2,000 years ago, a man measured our entire planet with just a shadow and a stick. Ancient astronomers achieved impossible accuracy long before modern tools existed, uncovering the true size of the Earth through sheer brilliance. By the end of this story, you will understand how a single observation under the Egyptian sun revealed a cosmic truth that reshaped human knowledge. How did they translate a simple shadow into a global measurement? And why were their results so startlingly close to what satellites confirm today? What does it say about our ability to solve grand mysteries with limited means long before any telescope pierced the night sky? Human eyes were already mapping the heavens. In the Fertile Crescent of Mesopotamia, along the life-giving Nile in Egypt, and on the rocky shores of Greece, ancient scholars turned their gaze upward not for idle wonder, but for survival. They watched the stars with a practical urgency, their observations woven into the very fabric of daily life. The reliable flooding of the Nile, essential for Egypt's crops, was predicted by the heliacal rising of the star Sirius. Sailors navigating the vast Mediterranean steered by the constellations. Religious ceremonies and the marking of sacred days were all tied to the rhythmic dance of the sun, moon, and planets. To serve these needs, they built the first observatories, structures like stone circles that tracked solstices with silent accuracy. They began compiling detailed catalogues of the stars and meticulously recording the wandering paths of planets against the fixed celestial backdrop. This was not a casual hobby. It was a systematic, generations-long project to decode the universe's clockwork. They recognized the patterns that governed the seasons, the length of a year, and the phases of the moon, turning chaotic skies into a predictable calendar. This relentless dedication to recording celestial movements, this foundational work of watching and noting, created a bedrock of knowledge. It was upon this solid foundation of accumulated data and proven patterns that a single brilliant mind could later stand to take the next audacious step and measure the entire Earth itself. That relentless project of celestial observation was about to find its ultimate expression in one man. In the intellectual heart of the ancient world, the great library of Alexandria, a scholar named Eratosthenes held the prestigious role of chief librarian. His mind was a repository of all the knowledge gathered across the known world, from Babylonian star charts to Egyptian land surveys, and it was from a simple piece of local information that he would weave together a revelation. He learned of a deep well in the southern city of Syene. On one specific day each year, the summer solstice, the sun at its highest point shone directly down this well, illuminating the water at the bottom without casting a single shadow. The sun was perfectly, absolutely overhead. This fact was interesting, but to most it was just a curious local phenomenon. For Eratosthenes, it was the first piece of a global puzzle. He realized that if the Earth were flat, a vertical object anywhere would cast no shadow under a noon sun. But in Alexandria, several hundred miles to the north, he knew this was not true. On that very same summer solstice, he went out and measured the shadow cast by a vertical stick, or gnomon. Sure enough, it cast a small, distinct shadow. The existence of that shadow in one city and its absence in another could mean only one thing. The surface of the Earth was curved, but Eratosthenes did not stop at this simple realization. He asked the next, more daring question: how curved is it? He understood that the angle of the shadow in Alexandria was the same as the angle between the two cities, measured from the Earth's core. It was a breathtaking leap of geometric insight. He measured the shadow's angle and found it to be about 7.2 degrees. Since a full circle contains 360 degrees, he reasoned that 7.2 degrees was exactly 1/50th of the circle. Therefore, he concluded, the distance from Syene to Alexandria must be 1/50th of the Earth's total circumference. All that remained was to measure that distance. He hired professional walkers, men trained to measure distances with consistent strides, to determine the overland route between the two cities. Their measurement gave him the final variable for his equation. He took that distance, multiplied it by 50, and arrived at a figure for the circumference of the entire planet. The result was staggeringly close to the value we accept today, a triumph of pure logic and observation. With just a stick, a shadow, and a brilliantly inquisitive mind, a man sitting in a library had reached out and measured the world itself. Eratosthenes' brilliant calculation was not born in a vacuum. It was the product of a sophisticated toolkit, a collection of instruments that transformed naked eye observation into precise, quantifiable data. That simple stick he used, the gnomon, was the most fundamental tool in the ancient astronomer's arsenal. By tracking the length and direction of its shadow throughout the day and across the seasons, they could determine the sun's altitude, the exact time of noon, and even the cardinal directions with remarkable accuracy. It was a humble tool, but in the right hands it revealed the tilt of the Earth's axis and the curve of its surface. For mapping the night sky, they developed more complex devices. The Armillary Sphere was a breathtaking work of art and science, a skeletal model of the cosmos made from interlocking bronze rings. Each ring represented a key celestial circle, like the equator or the path of the sun. By aligning this model with the actual sky, a scholar could track the movements of planets against the fixed stars, predict eclipses, and visualize the celestial mechanics that govern their world. It was, in essence, an analog computer for understanding the heavens, but observation required precise timing. How could you measure the angle of a shadow at the exact moment of local noon without a reliable clock? This is where water clocks or clepsydry came into play. These devices measured time by the steady drip of water from one container to another, marking the passage of hours with a consistency that sundials could not offer at night or on cloudy days. Coupled with the sundial's solar time, they created a framework for scheduling observations and comparing data taken at different times. The true workhorses for measurement, however, were the Dioptra and the later Astrolabe. The Dioptra was a sighting tube mounted on a calibrated disc, functioning like an early theodolite. It allowed surveyors and astronomers to measure the angular distance between 2 points, whether they were 2 stars in the sky or 2 landmarks on the horizon. The Astrolabe refined this concept into a portable, multi-purpose calculator. A user could suspend it, sight a star through its central rule, and read its altitude directly from an intricately engraved disc. With it, one could tell the time, determine latitude, and solve problems of spherical astronomy. Crafted from wood and bronze without a single lens or electronic component, these tools were marvels of mechanical ingenuity. Yet their true power was not in their individual complexity, but in how they were used together. An astronomer might use a water clock to note the time, an armillary sphere to predict a planet's position, and an astrolabe to measure its actual location. Every observation was meticulously recorded on papyrus or parchment, added to a growing library of data that spanned generations. It was this systematic combination of clever engineering and relentless record-keeping that provided the foundation for leaps of genius. Eratosthenes could only measure the Earth because he stood on the shoulders of centuries of accumulated technique and precision. Geometry gave the ancient astronomers their voice. It was the precise language that translated a shadow's slant and a well's depth into a cosmic truth. before a single measurement could be taken, the intellectual groundwork had been laid by minds like Euclid, who systematized the rules of shapes, lines, and angles in his seminal work, The Elements. These were not just abstract puzzles, they were a toolkit for decoding the universe, a set of proven principles that could be applied to the real, physical world. The secret to Eratosthenes' calculation lies in one of geometry's most elegant ideas, the properties of a circle. Think of the Earth not as a map but as a perfect sphere. Now draw two lines from the very center of the Earth, one reaching up to Alexandria and the other to Syene. The angle between these two lines, as seen from the core, is exactly the same as the angle of the shadow Eratosthenes measured in Alexandria. This is the magic of geometry. A local observation, a small angle measured between a stick and its shadow, directly revealed a global relationship. This is where the concept of similar triangles becomes vital. The geometry of the tiny triangle formed by the stick and its shadow in Alexandria is a perfect, scaled-down copy of the immense triangle formed by the Earth's radius and the distance to Syene. The ratios are identical, so by knowing one angle and one side of the small triangle, the shadow length, and one side of the large triangle, the distance between the cities, the entire system could be solved. Eratosthenes found that the shadow angle was 1/50th of a full circle. Therefore, the distance between the cities had to be 1/50th of the Earth's total girth. It was a breathtakingly simple and powerful application of pure logic. This mathematical framework transformed a curious local phenomenon into a planetary measurement. The absence of a shadow in a well in Syene was no longer just an interesting fact. It became a data point, a zero-angle reference that anchored the entire calculation. The nomen's shadow in Alexandria was no longer just a dark patch on the ground. It was a direct readout of the Earth's curvature. Geometry provided the bridge, turning two separate, earthly observations into a single, unified proof of a spherical world and its actual size. It demonstrated that the universe operates on mathematical principles, and that the human mind, armed with nothing but reason and observation, could discern those principles and use them to measure the impossible. The men who measured our planet were not isolated geniuses. They were part of a vast, interconnected web of human curiosity that spanned the globe. In the royal courts of Babylon, teams of scribes meticulously tracked the movements of planets, recording their data on durable clay tablets with a precision that would inform astronomers for centuries. Their work was a state-sponsored project, driven by the belief that celestial events were divine messages directly tied to the fate of kings and empires. Far to the east, in the scholarly halls of China, imperial astronomers developed elaborate star maps and calendars. Their mandate was to maintain harmony between heaven and earth, to predict the seasons for agriculture, and to alert the emperor to portentous events like eclipses, which were seen as a direct reflection of his mandate to rule. In India, scholars calculated the length of the year and the precession of the equinoxes with astonishing accuracy, weaving complex mathematics into their cosmological texts. This was a global endeavor, a chorus of different voices all asking the same fundamental questions about the world they inhabited. While Eratosthenes in Alexandria had the resources of the great library at his disposal, his Babylonian counterparts worked from ziggurats that doubled as observatories. Their methods and motivations differed, yet they were all united by a common goal to decode the cosmos. Rulers supported these efforts not merely for intellectual prestige, but for profound practical and symbolic reasons. A reliable calendar ensured stable harvests and tax collection. The ability to predict an eclipse or a comet could legitimize a ruler's power, demonstrating a unique connection to the heavens. This cross-cultural exchange of ideas was the true engine of progress. Babylonian eclipse records found their way to Greek scholars. Indian numerical concepts, including the revolutionary idea of zero, would later travel west. Each civilization built upon the discoveries of others, refining instruments and methods in a slow, collaborative accumulation of knowledge that spanned generations. The measurement of the Earth was not a single eureka moment, but the culmination of this ancient, worldwide conversation. Eratosthenes transformed a local curiosity into a universal truth through a sequence of brilliantly simple steps. His first crucial piece of data came from a deep well in the city of Syene. On the summer solstice, the sun illuminated the water at the very bottom, proving it was directly overhead and casting no shadow whatsoever. This was his 0 point, his baseline for a perfect vertical sun, but he knew the same sun at the very same moment would not be directly overhead in his own city of Alexandria, several hundred miles to the north. So he prepared a simple vertical stick, a gnomon, and on the appointed day he measured the small, distinct shadow it cast at local noon. The angle of that shadow was everything. By measuring the length of the shadow and the height of the stick, he could calculate the sun's angle away from the zenith, the point directly overhead. His measurement gave him an angle of about 7.2 degrees. This was the spark of genius. He reasoned that if the Earth is a sphere, then lines drawn from its center to Syene and to Alexandria would form that same 7.2-degree angle. Since a full circle contains 360 degrees, he divided 360 by 7.2. The result was 50. The distance between the two cities, therefore, had to represent 1/50th of the planet's total circumference. But how far apart were Syene and Alexandria? This was the final, practical variable. He needed an accurate measurement of the overland distance, a formidable challenge in an age without satellite imagery or precise surveying tools. Historical accounts suggest he used professional walkers, men trained to measure distances with a consistent, known stride. These human odometers paced the route, likely following the Nile, to determine the separation. While we do not know the exact figure Eratosthenes used, the principle was sound. He took that distance, let us say it was 5,000 stadia, and performed the final calculation. He multiplied it by 50. 5,000 times 50 equals 250,000 stadia. This was his answer for the Earth's circumference. When converted to modern units, his result was within a few percent of the actual value. Think about the elegance of this process. He took two localized observations, one shadow and one non-shadow, separated by a vast distance, and connected them with the unbreakable logic of geometry. He did not need to travel the world. He did not need complex machinery. He used a well, a stick, a measured stride, and a mind capable of seeing the entire planet in two small points of data. This methodical chain of observation, inference, and calculation is a timeless testament to the power of scientific reasoning. Roughly a century after Eratosthenes walked the halls of Alexandria, another Greek thinker turned his eyes to the stars to measure the world. Posidonius of Rhodes looked not to the sun, but to a brilliant beacon in the southern sky, the star Canopus. His method was a celestial variation on the same geometric theme. From his home on the island of Rhodes, he noted that Canopus, the second brightest star in the night, only ever just skimmed the horizon. It was a fleeting glimpse, a star that seemed to kiss the sea before disappearing again. But when Posidonius traveled to Alexandria, he saw something different. There, Canopus climbed higher, appearing clearly above the horizon. The same star, observed from two different latitudes, occupied two different positions in the sky. This discrepancy was the key. Just as Eratosthenes had used the difference in the sun's angle, Posidonius used the difference in the star's altitude. He carefully measured how much higher Canopus appeared in the Alexandrian sky compared to its fleeting appearance in Rhodes. This angular difference, he reasoned, represented the curvature of the Earth between the two cities. The principle was beautifully sound. If you imagine lines stretching from the center of the Earth to Rhodes and to Alexandria, the angle between those lines would be the same as the measured difference in the star's position. With this angle in hand, he needed only one more piece of information: the estimated distance between Rhodes and Alexandria. Using the maritime knowledge of the day, he plugged this distance into a geometric calculation similar to the one Eratosthenes had used. His final result for the Earth's circumference was different, and in fact less accurate than the earlier calculation, partly due to a less precise estimate for the distance between the cities. Yet the true significance of his work was not in the number itself, but in the powerful idea it demonstrated. Here was a completely independent method, using a star instead of the sun, that still pointed toward the same fundamental truth: a spherical Earth of a vast but measurable size. Posidonius and Eratosthenes were, in effect, cross-verifying each other's work across a gap of generations. This stellar approach underscored a profound versatility. It proved that the tools for understanding our world were not limited to the ground beneath our feet or the sun overhead. The entire cosmos could be used as a measuring tape, and the flickering light of a distant star could reveal the dimensions of our own planet. This new understanding of the Earth's true dimensions did not remain locked in a library. It sailed out to sea, transforming the ancient world's most perilous endeavor into a calculated science. With a reliable figure for the planet's circumference, mariners finally had a scale for their maps. A journey across the Mediterranean was no longer a vague leap of faith into the unknown. It became a measurable distance that could be planned for and provisioned. The greatest fear of any sailor, getting lost in a featureless expanse of water with no land in sight, began to lose its power. They could now estimate how far they had traveled and, more importantly, how far they had left to go, turning the terrifying void of the open ocean into a charted space. This leap in navigation hinged on a single, elegant concept: latitude. The same geometric principles that Eratosthenes used to measure the Earth became the sailor's guide. They learned to measure the angle of the North Star above the horizon with simple instruments. This angle, the star's altitude, was their latitude. A higher angle meant they were sailing north, a lower angle meant south. By maintaining a constant angle, they could sail east or west along a consistent parallel, holding their course even when out of sight of land for weeks. The sun served as a daytime reference, its midday height providing the same crucial data. This was celestial navigation in its earliest, most brilliant form, using the fixed stars and the predictable sun as a global positioning system. With this newfound confidence, trade routes expanded dramatically. The predictable sea lanes of the Mediterranean were now connected to more daring voyages along the coast of Africa and into the Atlantic. Goods, ideas, and cultures began to flow along these newly secure maritime highways. Spices from the east, tin from the north, and papyrus from the south moved with a regularity that was previously unimaginable. This was not merely about commerce, it was about the weaving together of human civilization. A merchant in Rome could plan a shipment to Alexandria with a reasonable expectation of its arrival, fostering a network of economic and cultural interdependence that stretched across the known world. Mapmaking evolved from symbolic art into a representational science. Earlier maps often depicted the world as a philosophical idea, centered on a particular empire or surrounded by mythical oceans. Now, cartographers could use the accurate Earth measurement to scale their creations. The distances between ports, the proportions of coastlines, and the true size of seas began to appear on parchment with a fidelity that would have been impossible before. These maps became practical tools for admirals and merchants, guiding fleets and shaping the strategies of empires. The theoretical sphere that Eratosthenes calculated was now being translated into a practical guide for human exploration, proving that the most profound ideas are those that find their way from the scholar's mind into the hands of the adventurer, forever expanding the boundaries of the possible. For all their geometric brilliance, ancient astronomers were working against a tide of practical difficulties. Their world lacked the standardized, laser-precise measuring tapes we take for granted. The very first step in Eratosthenes' grand calculation, the distance between Syene and Alexandria, was a major source of potential error. He relied on the estimates of professional walkers, men known as brightest, who counted their steps along the winding Nile Valley. While trained for consistency, their pacing could be thrown off by rough terrain, detours, or simple human fatigue. A small percentage of error in that initial distance measurement would be magnified 50-fold in the final result for the Earth's circumference. The tools of observation, marvels of bronze and wood, also had inherent physical limits. The edge of a shadow cast by a gnomon is not a perfectly sharp line. It bleeds and shimmers, especially in the heat haze of an Egyptian noon. Determining the exact point where the shadow ended was a matter of interpretation, introducing tiny but critical variations in the measured angle. At night, the twinkling of stars, caused by our own turbulent atmosphere, made precise celestial sightings a challenge. A star like Canopus, hovering near the horizon, would appear to dance and distort, complicating the clean angular measurements Posidonius needed. Even the most beautifully crafted Armillary Sphere or Astrolabe had limitations of resolution. The finely engraved scales on these instruments could only be read to a certain degree of precision. A craftsman's hand could only carve lines so close together, and the user's eye could only align a sighting rule with so much accuracy. These were not digital readouts, they were analog devices subject to the skill of the maker and the sharpness of the observer's vision. Perhaps the most profound assumption was treating the Earth as a perfect sphere. We now know our planet is slightly squashed, an oblate spheroid that bulges at the equator. This meant that a degree of latitude was not a constant value across the globe, a subtlety far beyond the measurement capabilities of the ancient world. This is why the results from Eratosthenes and Posidonius differed slightly from each other and from our modern value. These inconsistencies were not failures, but rather signposts on the long road of scientific progress. They highlight the messy human reality of discovery, where brilliant ideas must be executed with imperfect tools. Overcoming these obstacles demanded more than just intelligence, it required immense persistence. An astronomer might spend years refining a single measurement, building a more stable instrument, or waiting for the perfect atmospheric conditions to take a crucial sighting. This painstaking, iterative process of testing, finding error, and refining the method is the true engine of science. Their legacy is not a single, flawless number, but a powerful demonstration of how to pursue truth in a world full of limitations. The brilliant calculations of Eratosthenes and Posidonius could have vanished as easily as ink fading on papyrus. Their survival hinged on one of humanity's most fragile yet powerful inventions, the library. The Great Library of Alexandria was not merely a building filled with scrolls, it was the ancient world's intellectual engine room. Within its halls, a small army of scribes performed the vital, repetitive work of preservation, meticulously copying texts by hand onto new papyrus or more durable parchment. Every copy was a new lifeline, a safeguard against the inevitable decay of the original. This was a world without printing presses or digital backups, where a single fire or the bite of a worm could erase a century of thought. The library was a hub for scholars from across the known world, a place where Greek geometry met Egyptian land surveys and Babylonian star charts. Ideas did not just sit on shelves here, they collided and combined, creating new syntheses of knowledge. It was in this vibrant, collaborative environment that the foundational work on the Earth's measurement was codified, studied, and prepared for a journey it could not yet foresee. But even the greatest libraries are not immune to the tides of history. As the Roman Empire fragmented and the ancient world order crumbled, the flame of Greek science flickered dangerously low in Europe. Manuscripts were lost, libraries fell into disrepair, and the complex geometry of a spherical Earth began to fade into legend. The survival of this knowledge required a new guardian, and it found one in the burgeoning intellectual centers of the Islamic world. From Baghdad to Cordoba, caliphs sponsored massive translation movements, gathering scholars to render the great works of Greek science into Arabic. Ptolemy's monumental Almagest, which synthesized centuries of astronomical knowledge, was preserved and expanded upon by thinkers like al-Biruni, who himself made sophisticated calculations of the Earth's radius. In these new libraries and observatories, the Greek legacy was not merely stored, it was critically examined, corrected, and advanced. The chain of transmission was now unbroken, stretching from Athens to Alexandria and from Baghdad to the scholarly courts of medieval Europe. Centuries later, as Europe began to reawaken during the Renaissance, this preserved knowledge flowed back westward. Greek texts, which had been lost to the Latin West, were retranslated into Latin from their Arabic versions, often accompanied by insightful commentaries from Islamic scholars. This returning tide of ancient wisdom, now enriched by its long journey, provided the very spark for the age of exploration. Columbus studied these revived ideas of a spherical Earth, though he controversially interpreted the planet's size to be smaller, fueling his belief that he could reach Asia by sailing west. The endurance of a single measurement, from a stick's shadow in Egypt to a global understanding of navigation, is a powerful testament to the importance of cultural exchange. It underscores a profound truth about science, that it is not the product of one culture or one brilliant mind, but a collaborative human project that transcends empires and epochs, its survival depending entirely on our shared commitment to preserving and passing the light of knowledge. The mathematical principles these astronomers used were like a universal key, unlocking vast truths from small, local clues. At the very core of their success was the powerful concept of proportionality. This is the simple but profound idea that ratios and relationships remain constant, even when scaled up to immense sizes. The small triangle formed by a stick and its shadow in Alexandria maintained the exact same geometric ratios as the gigantic triangle spanning from the Earth's core to the two cities. This meant that measuring one angle and one distance on the ground allowed them to solve for the entire planet. It was a breathtaking application of scale, proving that the cosmos itself operated on consistent, knowable rules. Another crucial tool was the emerging science of trigonometry, the mathematics of triangles. While not yet fully developed into the complex tables we have today, its fundamental principles were already in use. By knowing the length of the shadow and the height of the gnomon, they could calculate the sun's angle with precision. This same logic applied to measuring the altitude of a star above the horizon. Every observation was translated into an angle, and every angle became a piece of a global puzzle. Where did this idea of dividing a circle into 360 degrees come from? This was a brilliant inheritance from Babylonian astronomers, who used a base 60 number system for their celestial calculations. This system was remarkably versatile, as 60 can be divided evenly in many ways, making the math of fractions and angles much simpler to handle. Adopting this Babylonian framework gave Greek scholars a ready-made and highly effective unit for measuring the heavens. It was this fusion of mathematical tools, proportionality, basic trigonometry, and a standardized angular measure that transformed their work from simple observation into rigorous science. They were no longer just describing what they saw, they were quantifying it. A shadow was no longer just a dark patch, it was a data point containing hidden information about the Earth's curvature. The different height of a star between two cities was no longer just a curious fact, it was a numerical value that could be plugged into an equation. This mathematical foundation empowered them to make an incredible logical leap, to infer global properties from strictly local evidence. With nothing but ratio and reason, they could stand in one spot and confidently pronounce the size of the entire world. So how close did these ancient thinkers actually get to the truth? The numbers themselves tell a stunning story. Eratosthenes concluded the Earth's circumference was 252,000 stadia. The challenge for historians is that the exact length of a stadion varied from place to place in the ancient world, but using the most likely conversion, his result translates to just over 40,000 kilometers. Our modern satellite measurements confirm the planet's circumference is 40,075 kilometers. This means Eratosthenes, working over 2,000 years ago, was correct to within a margin of error of just 1 or 2%. That is not merely close, it is a breathtakingly precise measurement achieved with the simplest of tools. Posidonius, using his stellar method, arrived at a similar figure, though his was slightly less accurate, likely due to the difficulty of precisely measuring the low-hanging star Canopus and the less certain sea distance between Rhodes and Alexandria. His result still fell within the same astonishing ballpark. When modern geodesy, the science of measuring the Earth, uses laser-ranging satellites and global positioning systems to map the planet's subtle oblateness, it is not overturning the ancient calculations. It is, in a profound way, confirming them. This level of agreement across millennia forces us to reconsider our assumptions about the past. It shatters the simplistic idea of a linear progression from primitive ignorance to modern enlightenment. These were not wild guesses or lucky accidents. They were the products of a rigorous, logical, and mathematically sophisticated scientific process. The ancient world possessed a profound and accurate understanding of the natural world, one that was not surpassed in its fundamental principles for over 1,000 years. Their achievement stands as a permanent testament to the power of the human mind to grasp the scale of the cosmos through observation, reason, and an unshakable belief that the universe operates by knowable laws. The night sky was far more than a spectacle for ancient civilizations. It was a living text. Every sunrise, every phase of the moon, and every wandering planet was a sentence in a cosmic story that dictated the rhythm of human life. This deep integration gave astronomy its urgency and its power. For a farmer along the Nile, the heliacal rising of Sirius was not an abstract event. It was a practical alarm clock signaling the imminent, life-giving flood of the river. His entire year, from planting to harvest, was choreographed by the stars. But this celestial influence reached far beyond the fields, straight into the halls of power. Kings and emperors relied on court astronomers to read the heavens for divine approval or warning. An eclipse was not just a shadow crossing the moon, it was a potent omen that could halt a battle, invalidate a coronation, or force a ruler into ritual seclusion to appease the gods. The sky was the ultimate authority, and its interpreters held immense political influence. This is why rulers invested so heavily in building monumental observatories. Structures like Stonehenge in England or the elaborate caracol at Chichen Itza were not merely scientific instruments. They were sacred sites where the practical need to track solstices merged completely with religious ceremony. At the precise moment the sun aligned with a specific stone doorway, it was both a confirmation of the calendar for planting and a direct communion with the divine. The very calendar that organized society was a product of this celestial observation. Lunar cycles defined the months for religious festivals and legal contracts, while the solar year set the framework for agriculture and tax collection. A society that could predict the seasons was a stable society, one that could plan, prosper, and expand. This search for order in the cosmos provided the constant motivation to watch, to record, and to measure with ever greater precision. The drive to understand the gods and to manage a kingdom is what ultimately funded the long, patient work that led to measuring the Earth itself. Their science was not a separate pursuit. It was woven into the very fabric of their quest for meaning, stability, and survival. This relentless quest to measure the heavens demanded a mastery of time itself. To capture the exact angle of a shadow at noon or note the precise moment a star crossed the meridian, ancient astronomers needed more than the sun's arc across the sky. They needed a clock that worked through the night and on cloudy days, a device that could slice the day into reliable, consistent intervals. The solution flowed from a simple principle: the steady drip of water. The clepsydra, or water clock, was a marvel of early engineering. Imagine a large ceramic vessel with a small hole near its base, filled to a marked line with water. As the water escaped into a second container, the dropping level against a series of internal marks would indicate the passage of hours. It was a constant, mechanical heartbeat for their observations. A night-long lunar eclipse could now be timed from start to finish, its duration recorded not in vague estimates, but in precise, comparable units. This allowed an astronomer in Babylon to note that a planet reached its highest point at the third hour of the night, and for a scholar in Alexandria to know they were looking at the same event at the exact same temporal coordinate. But water clocks did not work alone. They partnered with the sundial, the master of solar time. A sundial's moving shadow divided the sunlit day, clearly marking the crucial moment of local noon, when the sun reached its highest point and shadows were at their shortest. This was the anchor point for every daily measurement. Together, these two devices created a complete temporal framework. The sundial set the solar standard, while the water clock extended that standard into the dark and under overcast skies, ensuring the continuity of timekeeping. This precision rippled far beyond the observatory. For the sailor navigating by the stars, knowing the time from a water clock helped him calculate his position. For the farmer, the seasonal shifts marked by the sundial dictated the optimal days for planting and harvest, turning celestial patterns into agricultural abundance. Entire cities began to run on this shared, measured time, synchronizing markets, legal proceedings, and religious ceremonies. The development of these timepieces is a perfect example of how practical, earthly needs drove technological innovation, which in turn unlocked cosmic discoveries. You cannot measure the Earth without a stick and a shadow, but you also cannot do it without a reliable way to mark the moment that shadow is cast. The patient, drip-by-drip accumulation of measured time was the silent partner in every great calculation, the steady rhythm that made the measurement of space possible. That spherical Earth was not Eratosthenes' wild speculation, but a foundational belief among the learned. Centuries before his measurement, Greek philosophers like Pythagoras had already proposed a round world, arguing that the sphere was the most perfect and harmonious shape, a form worthy of the cosmos. But this was more than just philosophical elegance. Aristotle, a student of observation, laid out the evidence anyone could see. He pointed to the simple fact that during a lunar eclipse, the shadow the Earth casts upon the moon is always, invariably, a perfect curving arc. Only a sphere produces a circular shadow from every angle. sailors provided the most everyday proof. They watched as distant ships vanished from view, with the hull disappearing first and the mast tip sinking last, as if the vessel were slowly dipping behind a gentle, massive hill of water. This was not magic, it was the curvature of the sea. For the astronomers and mathematicians, this spherical model was not just an interesting idea, it was the essential operating system for their calculations. Without the assumption of a round Earth, Eratosthenes' method collapses. The geometric relationship between the shadows in two cities only makes sense if the surface between them is curved. The entire beautiful logic of his calculation, the similar triangles and the division of the circle, depends entirely on the Earth being a globe. This widespread acceptance reveals a profound truth about ancient science. It was not a collection of superstitious myths, but a discipline built on rational thought and observable evidence. These thinkers looked at the world, gathered the clues, and followed them to a logical conclusion. They trusted the testimony of a ship's mast and the pattern of a shadow on the moon. That trust in reason and observation is what gave them the confidence to take the next breathtaking step, to not only accept the Earth was round, but to actually reach out and measure it. Far across the Atlantic, under the dense canopy of the Central American rainforest, another civilization was mapping the heavens with its own unique brilliance. The Maya developed an astronomical tradition so advanced and so precise it stands as a monumental achievement of the human mind. At sites like Chichen Itza, they constructed El Caracol, a remarkable tower observatory whose narrow, strategically placed windows were perfectly aligned to frame the movements of Venus, the Sun, and the Moon. This was not a temple for passive worship, but a sophisticated instrument for active, relentless observation. Their entire society was organized around the celestial clockwork they so meticulously decoded. The Maya created a complex interlocking system of calendars that harmonized the solar year, the lunar month, and the cycles of Venus with an accuracy that startles modern scholars. The Hob, a 365-day solar calendar, guided their agriculture. The Tzolk'in, a 260-day sacred calendar, governed their rituals and ceremonies. And the long count calendar tracked vast epochs of time, allowing them to plot celestial events across millennia. This obsession with celestial timing was driven by a profound belief that the cosmos and human destiny were inextricably linked. They saw the planets not as distant balls of rock, but as gods whose movements directly influenced the fate of kings and the fortunes of harvests. The appearance of Venus as the morning or evening star was a moment of great portent, signaling times for war or peace. Because of this, their astronomers, the keepers of this sacred knowledge, held a position of immense power. They could predict eclipses, viewing them not as random events but as predictable moments when the cosmic balance was threatened. Their ability to forecast the retrograde motion of planets demonstrated a deep understanding of celestial mechanics, all achieved without telescopes or the geometric frameworks of the Greeks. How did they achieve such precision? Their tools were mathematical, built upon a base 20-number system and a revolutionary concept, the explicit use of zero. This sophisticated mathematics allowed them to perform the complex calculations needed to project cycles forward and backward in time, creating almanacs of the sky that stretched for generations. While there is no evidence the Maya sought to measure the Earth's circumference, their intellectual journey paralleled that of Eratosthenes and Posidonius in a profound way. They proved that the drive to comprehend the cosmos is a universal human constant. Isolated by vast oceans, they arrived at the same fundamental truth, that the heavens operate on a predictable mathematical order. One culture used geometry to measure the world, while another used cyclical time to master its place within the cosmos. yet both were answering the same eternal call to look up and understand. This philosophical shift did not happen overnight. A profound transformation in thought was required to move from seeing the world as a playground of unpredictable gods to viewing it as a cosmos, a term the Greeks themselves coined meaning an ordered and harmonious system. Before this, natural events like thunderstorms or eclipses were often explained as the direct actions of capricious deities, but a new breed of thinkers began to argue that the universe operated according to fixed, underlying principles that the human mind could actually uncover through reason and careful observation. Aristotle was a towering figure in this movement. He insisted that knowledge about the world must begin with the evidence of our senses, with what we can actually see, touch, and measure. He did not dismiss mythology, but he built a new foundation where logic and empirical data became the primary tools for understanding. Why did the stars move in such regular paths? Why did objects fall to the ground? These were not mysteries to be accepted on faith, but puzzles to be solved through systematic investigation. This belief in a knowable universe was the essential fuel for the astronomers' work. It gave them the confidence to spend years tracking planetary motions, convinced that behind the apparent chaos was a beautiful, mathematical order waiting to be decoded. This intellectual revolution was institutionalized in places like Plato's Academy and Aristotle's own Lyceum. These were not just schools, but vibrant research centers where scholars lived, debated, and collaborated. Within their colonnaded walkways, ideas were rigorously challenged. A theory about the planets was not simply stated. It had to be defended against counterarguments and tested against observed reality. This culture of critical debate was a powerful engine for refinement. It forced thinkers to sharpen their logic, to seek better evidence, and to discard explanations that did not hold up to scrutiny. It was this very environment that nurtured a mind like Eratosthenes. His calculation of the Earth's circumference was not a bolt from the blue. It was the natural, almost inevitable product of a system that valued measurement over myth, that encouraged bold questions, and that provided a community of peers to vet and validate extraordinary claims. The stick and the shadow were his tools, but the Greek philosophical tradition was the bedrock upon which he stood. It was the marriage of this relentless curiosity with a disciplined method that allowed humanity to take its first precise measure of the world. That simple shadow cast by a stick in Alexandria was far more than a dark patch on the ground. It was a direct line to the center of the Earth and a numerical key to our planet's true size. The length of that shadow, when compared to the height of the stick, revealed a precise angle, the angle at which the sun's rays were striking that specific point on the globe. But a single shadow is just a local curiosity. The revelation came from comparing two shadows, or rather, one shadow and one non-shadow, separated by a vast distance. In Syene, at the very same moment, there was no shadow at all, meaning the sun's rays were striking the Earth there at a perfect 90-degree angle. In Alexandria, the rays hit at a slight slant, creating that measurable shadow. The difference between a 90-degree impact and, say, an 82.8-degree impact was everything. That angular difference, a mere 7.2 degrees, was not just a local measurement. It was the very same angle you would get if you drew two lines from the center of the Earth, one reaching up to Syene and the other to Alexandria. The local phenomenon was a perfect, scaled-down mirror of the global reality. This is where trigonometry performed its magic. The geometry of the small triangle formed by the stick and its shadow was identical in its proportions to the immense, imaginary triangle formed by the Earth's radius and the distance to the other city. Knowing one angle and one side of the small triangle allowed them to solve for the entire system. The 7.2-degree angle was 1/50th of a full circle's 360 degrees. This meant the distance between the two cities had to be 1/50th of the Earth's total girth. A measurement that could be walked by a human in a matter of weeks was suddenly, irrevocably, tied to the dimensions of the entire planet. The shadow was no longer just a shadow. It was a cosmic ruler, a tool that translated a few hundred miles on the ground into a definitive scale for the world. This elegant leap from the particular to the universal is what separates simple observation from profound science. It is the ability to look at a sliver of darkness at your feet and see in it the gentle, massive curve of the Earth itself. The rediscovery of a single manuscript could shatter 1,000 years of belief. As the Renaissance dawned, long-lost texts by Greek and Arabic scholars began to flow back into Europe, carried by scholars fleeing a falling Constantinople and translated in the vibrant new centers of learning. These were not mere curiosities, they were intellectual dynamite. Among them were the very works detailing the methods of Eratosthenes and the spherical Earth models of Ptolemy, ideas that had been preserved and refined in the Islamic world while Europe had largely forgotten them. Suddenly, scholars like Nicolaus Copernicus had access to a complete, sophisticated system of celestial mechanics that challenged the very center of the universe. He did not invent heliocentrism from nothing. He was re-evaluating ancient ideas from Aristarchus of Samos through the powerful new lens of Renaissance observation. The precise, mathematical approach of the Greeks gave him the courage to propose a sun-centered system, arguing for its mathematical elegance and simplicity over the cumbersome Ptolemaic model. This was the true spark of the scientific revolution, not a rejection of the past, but its fulfillment. The ancient quest to measure the Earth was reborn in new geodetic experiments, as cartographers and navigators, armed with Eratosthenes' principles, sought to create ever more accurate maps of a world that was rapidly expanding. The tools evolved, but the foundational geometry remained the same. Then came the telescope, a technological leap that extended human vision in an unprecedented way. When Galileo Galilei turned his spyglass to the heavens, he was not just seeing new things, he was testing ancient ideas with new power. He saw the moons of Jupiter, a miniature solar system that challenged the old geocentric order. He observed the phases of Venus, which could only be explained if it orbited the Sun. His discoveries were a direct conversation with the past, using a new instrument to answer questions the Greeks had first posed. This was the ultimate integration, the marriage of ancient philosophical inquiry with emerging empirical technology. The legacy of those early astronomers was not a set of answers, but a method, a way of questioning the world that proved more valuable than any single fact. Their work demonstrated that knowledge is a collaborative project stretching across cultures and centuries, where each generation stands on the shoulders of the giants who came before, seeing just a little further into the cosmic dark. The idea that everyone believed in a flat Earth until Columbus sailed is one of history's most stubborn myths. Educated scholars across ancient Greece, the Islamic world, and medieval Europe had known our planet was a sphere for over 1,000 years. They saw the evidence in the curved shadow on the moon during an eclipse and in the way ships vanished hull first over the horizon. This was not a secret but common knowledge among the learned. Columbus's famous voyage was not a debate about the Earth's shape, but a fierce argument over its size. He was using an estimate smaller than Eratosthenes' more accurate calculation, believing the journey to Asia was feasible. His critics, who knew the classical measurements were likely correct, thought he would run out of supplies long before reaching his goal. They were right about the distance, of course. America just happened to be in the way. Another common misconception paints their astonishing accuracy as a lucky guess. How could a man with a stick possibly get so close to the modern value without advanced technology? The answer lies not in luck, but in a rigorous, repeatable method. Eratosthenes' process was a chain of logical steps, from the initial observation in Syene to the geometric calculation in Alexandria. His result was not a single, fragile number, but the output of a verifiable scientific procedure. If you repeated his steps with precise modern instruments for measuring distance and angle, you would get an even more accurate answer. Their success was a product of design, not accident. Perhaps the most limiting myth is the focus on a single Western narrative. While the story of Eratosthenes is a brilliant chapter, it is just one page in a global library. Babylonian astronomers kept detailed records on clay tablets for centuries. Indian mathematicians calculated the Earth's diameter with impressive precision. The Maya, isolated across an ocean, built observatories and tracked planetary cycles with a calendar more accurate, in some ways, than the one used in Europe at the time. This was a worldwide human endeavor, a chorus of curiosity rising from every continent. Dismantling these myths does more than just set the historical record straight. It forces us to confront our own biases about progress. We often assume that older means more primitive, that our ancestors were less intelligent or less capable of complex thought. The story of ancient astronomy proves the opposite. It shows us that human brilliance is not a modern invention. By judging the past on its own terms, by looking at the evidence they left behind, we gain a profound respect for the intellectual giants who, with simple tools and powerful minds, first measured our world. The stars gave ancient astronomers the questions, but mathematics provided the language for the answers. This was not a casual partnership, but a deep, symbiotic relationship where each field pushed the other to new heights. The very geometry used to measure a farmer's field was stretched to a cosmic scale, forcing the invention of an entirely new branch of mathematics, spherical geometry. On a flat surface, the angles of a triangle always add up to 180 degrees, but on the curved surface of a sphere, like the Earth or the celestial dome, this rule breaks down. Navigating by the stars or calculating the sun's path required understanding triangles drawn on these vast, invisible curves. This was mathematics evolving in real time to solve a practical, heavenly problem. The drive to map the planets created an insatiable demand for more sophisticated calculations. Simply watching the wanderers was not enough. Scholars wanted to predict their positions years, even decades, into the future. This required modeling their complex loops and pauses against the backdrop of fixed stars. The old methods were no longer sufficient. In response, the astronomer Hipparchus of Rhodes compiled the first known trigonometric table, a tool that directly linked the length of a chord in a circle to its corresponding angle. He did not create this for abstract pleasure. He built it as a precise calculator for astronomy. With his chord table, he could translate angular measurements taken from the sky into linear distances, predicting planetary positions with a new level of accuracy. This is the perfect example of the feedback loop between observation and theory. An astronomical observation revealed a gap in mathematical tools. The creation of those tools then enabled more precise astronomical modeling, which in turn revealed new celestial behaviors to be explained. The Armillary Sphere, with its interlocking rings, was a physical model of this spherical thinking, a three-dimensional representation of the cosmos that could only be built and understood through geometric principles. The calculation of the Earth's circumference by Eratosthenes is the ultimate testament to this interdisciplinary triumph. It was not just an astronomical observation or a mathematical trick. It was the fusion of both, a celestial event interpreted through geometric logic. The sun's position was the astronomy, the similar triangles and circle division were the mathematics. One was meaningless without the other. This synergy demonstrates that the greatest mysteries are rarely solved within the boundaries of a single discipline. It is at the intersections, in the fertile ground where stars meet numbers, that humanity finds its most profound and accurate truths. Their calculations began to reshape the very fabric of daily life, reaching far beyond the scholar's study. The most immediate impact was on the land itself. With a reliable figure for the Earth's circumference, mapmakers could finally produce scaled charts of coastlines and territories. A governor planning a new road or a canal could now estimate the required materials and labor with unprecedented accuracy. Military commanders used these improved maps to plot campaigns, calculating marching distances and supply lines with a new level of strategic confidence. Trade exploded as merchants could now plan voyages with a realistic understanding of the journey's length, leading to more reliable deliveries of grain, olive oil, and exotic goods that fueled urban economies. This was no longer abstract geometry, it was the blueprint for managing an empire. The rhythms of agriculture were also guided by this celestial knowledge. Calendars refined through astronomical observation told farmers the optimal window for planting and harvesting. Knowing the precise length of the solar year meant a community could align its agricultural cycle with the seasons, maximizing crop yields and ensuring food security for growing cities. A miscalculation of even a few days could mean the difference between a bountiful harvest and a devastating famine. The sky became a reliable clock for the most essential human activity, feeding itself. On the open sea, the principles of celestial navigation turned terrifying voyages into calculated journeys. Sailors using simple versions of the astrolabe could determine their latitude, allowing them to traverse open water instead of clinging fearfully to the coast. This newfound confidence unlocked new trade routes across the Mediterranean and beyond, weaving a web of cultural and economic exchange that connected distant civilizations. Ideas, technologies, and artistic styles flowed along these maritime highways, enriching every society they touched. Even the design of cities reflected this cosmic order. Major streets were often aligned with the cardinal directions, determined by the motion of the sun. Temples and public buildings were frequently oriented to capture the sun's rays on a significant day, like the solstice, blending spiritual symbolism with practical illumination. The theoretical knowledge of a spherical Earth measured through shadows and stars was thus woven into the tapestry of civilization. It made governance more effective, travel safer, harvests more reliable, and cities more harmonious. This tangible utility is precisely what ensured these discoveries were not forgotten. A useful truth is a treasured possession, copied, taught, and passed down through the ages, because a society that understands the measure of its world is a society built to last. Their impossible accuracy was built upon a mountain of meticulous notes. Night after night, year after year, ancient astronomers committed themselves to the patient work of watching and recording. They did not simply look at the sky, they measured it, charting the precise positions of stars and planets against grids they inscribed on their instruments. This was not a casual hobby but a systematic, data-driven pursuit. They tracked the cycles of Venus, timed the duration of lunar eclipses, and logged the changing altitude of the sun with a relentless consistency. Every shadow length, every star rising was a data point to be collected and compared. This long-term accumulation was their greatest asset, allowing them to see beyond fleeting anomalies and grasp the deep, repeating patterns of the cosmos. Over decades, the tiny discrepancies in a planet's path became visible, revealing the subtle wobbles and loops that simple models could not explain. They were not just collecting facts, They were building a library of evidence against which every theory had to be tested. If a new model of the solar system predicted a planetary position that did not match their centuries of recorded observations, the model was discarded or refined. This commitment to empirical evidence over pure speculation marked a profound shift in human thought. It was the move from explaining the world through stories to explaining it through measurable, repeatable data. The angle of a shadow was not open to philosophical debate. It was a physical fact. The time a star crossed the meridian was a number that could be verified by anyone, anywhere, with the right tools and training. This grounding in observable, quantifiable phenomena is what separates their work from myth and gives it such enduring power. Their calculations stand the test of time not because they were lucky, but because they were built on a foundation of unshakable evidence, patiently gathered under the open sky. A single idea, born under the Egyptian sun, was never destined to remain in one library. It began a silent journey carried on camel trains along the Silk Road and in the hulls of trading ships crossing the Indian Ocean. Greek astronomical texts filled with geometric proofs and theories of a spherical Earth traveled eastward. In the sophisticated scholarly centers of India, these ideas were not merely copied, they were absorbed and transformed. Indian mathematicians, masters of their own complex systems, encountered Greek geometry and saw new possibilities. They refined calculations for planetary motions and incorporated this foreign knowledge into their own cosmological models, creating a richer, hybrid understanding of the heavens. The transfer was not one way. The revolutionary concept of zero, along with the decimal system that we use today, began its journey westward from Indian thinkers, carried by merchants and scholars into the heart of the Islamic world. There, in cities like Baghdad and Damascus, a monumental project of translation was underway. Caliphs sponsored houses of wisdom where teams of scholars rendered the entire body of Greek science into Arabic. But they did more than just preserve these scrolls, they interrogated them. The Almagist Ptolemy's great work on the cosmos was not taken as gospel. Astronomers like Al-Batani made his own, more accurate observations, correcting Ptolemy's figures and refining the models. They built larger observatories, crafted more precise instruments, and compiled star catalogues that far surpassed their Greek predecessors. This was knowledge in motion, constantly being tested, challenged, and improved as it passed from one culture to the next. A star chart drawn in Babylon might be studied in Alexandria, copied in Baghdad, and then carried by a traveler to a monastery in medieval Spain, where a monk would translate it from Arabic into Latin. With each handoff, the map was slightly corrected, a star's position fine-tuned, a constellation renamed. This slow, collaborative editing across centuries and continents created a collective body of knowledge that no single civilization could have built alone. It stripped away regional biases, proving that a geometric proof holds true whether you are standing on the banks of the Nile, the Indus, or the Tigris. The light from a star belongs to no empire, and the logic that measures its path is a universal language. This relentless, borderless exchange was the true engine of discovery, a quiet testament to the fact that the greatest human achievements are never solitary, but are built from the shared curiosity of the entire world. Their legacy is not locked away in dusty manuscripts, but lives on every time we glance at a map or trust a global positioning signal. The brilliance of Eratosthenes and his peers demonstrates a timeless truth that profound discovery often begins with observing the ordinary world with extraordinary insight. A stick, a shadow, a single star on the horizon, these were the humble keys that unlocked the dimensions of our entire planet. They achieved the impossible not with advanced technology, but with the most powerful tools available, a curious mind and an unwavering trust in mathematical order. This was more than a measurement, it was a revolution in human thought, a declaration that the cosmos could be understood through reason and careful observation. That foundational shift paved the way for everything that followed, from the daring voyages of the age of exploration to the precise orbital calculations that guide our satellites today. We are the beneficiaries of that ancient global conversation, a chain of knowledge that stretches from the libraries of Alexandria to the palm of your hand. So the next time you look up at the night sky, remember that you are part of that same enduring story of curiosity. What seemingly simple observation in your own world might contain a hidden truth waiting to be measured? We would love to hear your reflections in the comments below, and if you enjoyed this journey into the past, subscribe for more explorations of the incredible ideas that shaped our world.